Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to our chapter 6 lecture. This is going to be on cases, and as usual, I will split the chapter into three sections: part A, part B, and part C. Make sure you watch all the recordings before you complete the Alex assignment. Module 6 is for chapter 6 cases. Remember that. So part A, this is the outline for part A. We look at section 6.1, supersonic skydiving and the risk of decompression. Look at the concept of pressure, the result of molecular collision. Section 6.3, the three CAS laws. I know in Intro to Chemistry, you may have covered some of the laws we will look at in 6.3. And lastly, in part A, we will look at the ideal CAS equation or ideal CAS law. I have my whiteboard. I'll show you once we get in there on calculation. Make sure you have a piece of paper and a pen. Those will be some equations. I'll share with you some concepts. I'll share with you, which I will expect you to recall when taking the quiz as well as the exam. The author talks about the supersonic skydiving and the risk of decompression. When we talk about the decompression, skydivers wear or put on a pressurized suit. You see this? This is somebody who is diving free fall for 4 minutes, 27 seconds at the top speed of 1,322 kilometers. This is some information regarding someone who dived from this altitude. At the outer space, the pressure is so low that skydivers have to wear a pressurized suit with the pressure similar what we have on Earth. Other than that, if the pressure is low or if something happened to this suit, see here, the pressure will be low and the divers or skydivers risk the decompression. The lungs will expand as a result of being exposed to the vacuum. I hope you recognize that in the outer space out there, the pressure is so low. You may have heard about incidences where the airplane or planes basically make emergency landing if the cabin pressure runs low. This is just a small, readout. You can read more on decompression on 6.1, which relates to the pressure. Before we look at the pressure, let's look at the properties of gases compared to other solid state. Properties of gases compared to solids and liquid. Let's say this is solid and this is liquid. If I do have some diagram here to represent solid, liquid, and gas, you can or you should be able to see the difference between the three diagrams right here. In gases, there is large intermolecular forces. Liquids, the molecules or atom roll over one another, whereas in solids, the atoms or molecule are rigid, they are in a fixed position. So here you need to know samples of gases or just the gas assume both shape and volume. I can summarize this as shape, all right, volume. You may want to use this diagram for solid, liquid, and gas. They have their own shape, they have their own volume. They have their own volume, but they don't have the shape. But for gases, They do not have their own volume nor shape. They assume the shape of the container, all right? Gases are compressible. Why is it compressible? Because there is large intermolecular forces. If you look at here, this is called molecular space. All right, there is large intermolecular space which you can compress, but for solid and liquid, they are in contact and you cannot compress. Densities for gases compared to condensed matter, that is solid and liquid, they are much smaller compared to those of solid. Density for gases, they are expressed in grams per liter. This is density. But for solids and liquids, all right, this is expressed in grams per ml or grams per cubic centimeters. They are low. Gases also form a homogeneous mixture. Remember homogeneous mixture? We looked previously. Homogeneous mixture. They form uniform. They have definite properties with one another. In other words, they have or they form one phase. For example, where I am right now, or where you are, the air in the space is a mixture of several gases: nitrogen, oxygen, CO2, H2O in gaseous state, but they form a uniform mixture. So remember that we use this property in some of the gases we look at. What you expect to see or what you expect to see in an exam or a quiz is which one of the following statement about gases is false. What I'm trying to highlight here is you should be well-rounded in properties of gases compared to solids and liquid. We didn't talk about non-reacting gases mixtures are homogeneous. Yes, they don't react. Gases expand spontaneously to fill the container. That's correct. A is correct. P is correct. But here, C, all gases are colorless and odorless. This is not correct. It is false. Some gases, they have color, such as nitrogen dioxide. It's reddish brown color. The chlorine is a greenish color. Please make sure that you know the properties of gases compared to solid and liquid. Yes, large intermolecular forces. Large intermolecular space, right? Compared to individual molecules, they have large intermolecular spaces. Because of that, gases are compressible. You can make your own notes on properties of gases. These are just few common. These are few common gases you need to know. I got this from lecture PowerPoint slide I used in the previous section. We don't have this, but just to give you an idea that gases are they are not all colorless. Look at this: nitrogen dioxide, reddish brown. Okay. I won't, or I don't expect you to memorize their colors, to memorize their properties. Let's see. Before we look at the pressure, there are four parameters which define the state of gas. And here they are, which I want you to take note of what I'll be using later on. Sorry about that. Temperature, I'm going to be using T. Pressure, you're going to be using B, simple, and volume, going to be using V. And lastly, amount here. Amount, when you say amount of gas, we'll be using, and this is the number of moles, where N is the number of moles of gas. So these are the four properties we define a sample or the state of a gas, whether it is solid, whether it is liquid or gaseous. We have looked at or discussed the three of these four. The temperature, remember when we have to convert the temperature from degrees Celsius to Kelvin, all right, from degrees Fahrenheit to degrees Celsius and so forth. We discussed that before, but pressure, this is the first time we are looking at. Volume, we also look at volume in section 1.6, measurement and dimensional analysis. You should be able to find the volume of a substance or an object. Number of moles, all right? Remember number of moles, unless given number of moles, you should recall the formula, all right? Mass in grams of molar mass. We looked at this equation before, and this is given, or this can be, the denominator can be given, or you may need to use the periodic table and formula. All right. So you need to have the formula for the gas, and using the periodic table, you should be able to calculate the number of moles. So the three P mentioned here is the number of moles, volume, and temperature. But we're going to look at the number two, pressure. This leads us to section 6.2, pressure, and it is simply defined as the force exerted by unit area, or just pressure is given by force over area. Force over area. And when we talk about that, the pressure exerted by a sample of a gas is simply the force exerted by gas molecule bombarding on the wall of a container. Constantly there are gas molecule in the atmosphere pumping or bombarding onto the surface of anything. It could be the table, even it could be you. When we talk about the atmospheric pressure, they are air molecule or air particles pumping onto the wall or on any surface. Just as a pole exerts a force when it is bounced against the wall, gaseous atoms or molecule exert force also when it collides with the surface. This is what causes the pressure. When you feel your flat tire, the bicycle or your car flat tire, adding in air, all right, it means you are adding more molecules, more particles into the tire. And what causes the pressure to go up is the molecule or atoms bombarding or bouncing on the wall of the tire. Sometimes you may have seen this picture when they talk about the weather of the day, low, high. Variation in pressure on the Earth atmosphere creates wind and pressure. Where H here on the picture indicates the region of high pressure usually associated with clear weather. This is the region with low pressure usually associated with the unstable weather. And this has to do with the atmospheric pressure, which we'll see later on how to measure that. So this is what I explained in the previous slide, what causes pressure, to, or how we define the pressure. It's just the constant movement of gas molecules colliding on the surface of anything or any surface around them. The pressure of a gas depends on one number of gas particles in a given volume. So that if we have a container here with only two, and a container, even if it is the same, with more molecules, of course, this will be the low pressure. This will be the high pressure. Number of gas particles in a given volume increase the pressure. The volume also, even if we have to here to increasing the volume will lower the pressure. We'll see that. And also the average speed. All right. We will see later on how temperature affects the speed of a sample of a gas. We have looked at the those three factors. What I want to fast forward to is when we talk about the pressure, how do we measure the pressure of a sample of a gas? All right. Before we look at the calculation, here is an illustration what happened. Some of you may have experienced a little bit pain when the plane is descending or when the plane is landing. This has to do with the pressure outside and the pressure inside your eardrum. If you look at this diagram, we have high concentration of gas molecules, whereas outside we have less, which means this is the area of low pressure, high pressure. And when this happens, it will cause bulging of the eardrum and you will experience a little bit of pain. I've experienced this myself every time I fly. And that has to do with the difference in pressure, the pressure imbalance in the ear. Next time you experience this, please remember that it has to do with the difference in pressure inside and outside. Now, going back to the atmospheric pressure and how it is measured, a barometer is an instrument used to measure the pressure or atmospheric pressure. It is simply an evacuated glass tube, all right? The tip of which is submerged in a pool of mercury. You know, the element mercury on the periodic table. The atmosphere or the atmospheric pressure on the liquid. This is the pressure of, this is the barometer used for that. Sorry about that. This is the barometer with the liquid mercury inside, with this side is closed with liquid mercury on the container. At sea level, if this is completely filled with mercury, the meniscus, and this is open, this is closed, the meniscus will be 760 millimeters or 76 centimeters in height. This is the mercury, and basically what is holding the mercury inside this long glass tube is the atmospheric pressure. This 760 you'll see quite often. This is at sea level, at sea level. The liquid mercury inside, let's say we evacuate this completely filled with mercury, a long glass tube with 1 centimeter in diameter, inside it in a container with the mercury, the meniscus will drop 760 millimeters or 76 centimeters, all right, or 29.92 inches. from the surface of the liquid mercury in a container. This is how the parameter works. It's used for measuring, all right? Parameter. This is an instrument used to, all right, this is an instrument used to measure atmospheric pressure. Atmospheric pressure. It was invented by Torresol, all right? Invented Evangelista, all right? Torricelli, all right? Invented by Evangelista Torricelli. He was an Italian scientist, came up with this. So if you look at this distance right here, let's see. From the surface of the liquid mercury to the meniscus. Remember, this was initially evacuated, it was completely filled with mercury, but upon inverting this or placing in a container with liquid mercury, the atmospheric pressure is preventing or holding on the liquid mercury inside the glass tubing. And at sea level, all right, at sea level, the distance from the surface to the height of the meniscus here is 760 millimeters or 29.92 inches or 76 centimeters, whichever way you look at it. And next time you see that, it has to do with the height of the liquid mercury in a parameter. Of course, changing the location, this distance, the height will change depending on the altitude, depending on the altitude. These are common pressure units, all right? And the equivalent statement you see here, I'll give you in the exam, but you should be able, you may not have it in Alex assignment, but you should know that this is one large equivalent statement which states that 1 atmosphere equals 760 torr, T-O-R-R. This is in honor of Evangelista Torresol, or 760 millimeter mercury. Remember, the mercury is the element inside the glass tipping, or 14.7 pounds per square inch, or 29.92 inches. That's the height again of the liquid mercury inside the glass tubing, or 101.325 kilopascal. This equivalent statement will be used to convert the pressure from one unit to the other unit, just the way we did before in dimensional analysis. Once we get to one of them, for example, this one, let's see how we can convert the given pressure to millimeter mercury. At the outset, a pressure of 0.500 atmospheres is the same as, take note of the units and the significant figures as well. So this is 3 significant figures. From the dimensional analysis, we generate a conversion factor that we want to get rid of atmospheres. What we are looking for is millimeter mercury, of which we need to go back to this slide right here, that 760 millimeter mercury equals to 1 atmosphere. So here is 760 millimeter mercury. This is 1 atmosphere. We cancel that, and the units for that, we should be able to get 380 above that. This is 380 millimeter mercury. This is 380 millimeter mercury. So next time you may see, changing from atmospheres to pounds per square inch or pounds per square inch to torrs or inches mercury to kilopascal and so forth. So generate your own conversion factor so that you can plug in unit cancellation and you remain with what you are looking. Always remember to type the unit. Just like in the previous lectures, I always suggest problems you need to practice with in pressure conversion. Look at problem number 25, 27, 29 on page 255, and I believe 256 in the text. This will give you a good practice on pressure conversion, Let's move on to pressure measurement of a sample of a gas. In the previous section, it was pressure measurement of, atmospheric pressure and converting from one unit to the other unit using the right conversion factor. Now, a manometer is used to manometer. What is a manometer? This is an instrument used to, all right, this is an instrument used to measure a sample of a gas. So it's not like the barometer. This one is used in measuring a sample of a gas. All right, sample of a gas. Should know how it works, all right? So the difference between the two, this manometer for a sample of a gas, whereas barometer is used to measure atmospheric pressure at any given time. There is a diagram for a manometer here. We should know how it works. The P atmosphere here, this is the atmospheric pressure. It's open. So that means there is force exerted on the liquid mercury. Look at this. This is liquid mercury. The black one you see here is the liquid mercury. Atmospheric pressure, air molecules or particles from the atmosphere is bombarding the surface of the liquid mercury here. Our sample of a gas is enclosed. So you can imagine if the sample of a gas has high pressure compared to the atmospheric, and when you open the valve, of course, air will try to escape. It's going to push the liquid mercury. So by looking at this, I can tell that the pressure is higher. Pressure in this manometer is higher than the atmospheric pressure because it's exerting. You see the label, the meniscus on the left side, not the one exposed to the atmosphere, is low because of the pressure of a sample of a gas. If the pressure of a sample of a gas is low, of course, the atmospheric pressure will push this. It will be the opposite. This will be up somewhere here, and this one will be low here if the sample of a gas is low. So the way it stands right now, I don't want you to think or assume that always this is the equation for determining the pressure of a sample of a gas. It turns out that for this illustration, the pressure of a gas is higher than the atmospheric. So we add. If it is the other way around, we subtract, okay? You subtract. In other words, if this was high here and this was low, this will be pressure of a gas is given by the atmospheric pressure minus if it was, but because it's high, we add for that. we add for that. That's how the manometer actually works. And here we're talking about the competition being established for the sample of a gas here. That's the pressure here and the pressure in the atmosphere. The difference here is used to calculate change in H right here. All right. Is used to add that pressure for H here. You use to add to that to get the what? The pressure of a sample of a gas. We look at the example on how it works. Still the same diagram. If the pressure, look at this pressure here is for the atmosphere, which is given here as 764.7 torrs, which is the same as a millimeter. All right. Now, a sample of a gas is placed in a flask tied to an open-ended mercury. So this is the sample of a gas tied to open-ended, this figure. And a meter stick is used to measure the height of the mercury in two arms. The height of the mercury in open-end arm is, so this is the height, and this is the height for this. This height you see here is for the one on the manometer, the closed side. This is the open side. The height of the meniscus is 136.64. The question is, what is the pressure of a gas in the atmosphere or in kilopascal? All right, kilopascal, given the statement for that. Atmosphere. So far, what you need to know is, let's see from the whiteboard here, one thing you need to see or understand is the pressure of a gas is greater. So this is the equation we are going to use. And H is given by 134, no, 136, not 134, 136.4 millimeters minus 103.8 millimeters. So you subtracted 2 to get the height. So that pressure height here, you'll add to 764.7 torrs. So here is the solution for that. Understand how that works to find the H is the difference between the two. So this is how you will proceed. In that case, pressure of a sample of a gas, we have to add the H. This is the atmospheric pressure. Where we got this, we were given here, all right? The pressure of the atmosphere exposed at 764, and the height, 134 minus 103, is because of this height. Remember, always you need to find the height here, no matter what. The only difference is when do you subtract, when do you add. If the pressure is low, you subtract. If the pressure is high, the way it is, we add. And that's why here we are 764.7 torrs for the atmosphere plus the difference, and that is the atmospheric pressure in torrs. And to convert to atmospheres, you need to remember or recall that 1 for 760 TORR equals 760 millimeter mercury. All right, which is the same as 1 atmosphere. It's the same as 1 atmosphere. So if we want to change torrs to atmospheres, these are the two conversion factor, two equivalent statement we will use, because 1 ATM, need to know this is 760 TORR, and then you set up the equation, convert to atmospheres. That's how a manometer works. You will see this in the quiz. You will see in the exam how to use the manometer, and of course the kilopascal here, we're gonna generate that 1 atmosphere. This is from this equivalent statement here. that kilopascal. You see 103 equals to that, which means going to be our conversion factor here to change to kilopascal. So please check. Here is another example on how to illustrate it. That it means you should be able to complete problems similar to what I do have here. How do we calculate the pressure of a sample of a gas? It's the same as the one we had before, which means here 764.7 TORR is the PATM for the atmosphere. From this diagram, it seems it shows that the pressure of a sample of a gas is greater than the atmospheric pressure. So for PO gas, the pressure of a gas is given by PO atmosphere, ATM, all right, plus P of the height, which is this height right here. This is slightly different from the one we had, even though it looked the same. All right, same diagram, even same, but there is a statement here that if the pressure of a gas inside the flask here were increased and the height of the column on the open-ended arm went up by 5.0 millimeter, what will be the new? You need to understand that if this is the diagram of a manometer, all right? So if this end is going up by 5 millimeters, this side also should be going down by 1 millimeter. I mean 5 millimeters. So down here will be 103.8 millimeter minus 5, because it is coming down. So if that one is coming down, all right, that's going to be 103.8 minus 5. This is millimeter. It's coming down because the pressure here is high. So this will come down by 5, while this one is going up by 5. So at the top here will be 136.4 millimeter plus 5.00. This is going to be 4.141 millimeter mercury. So we know our height. So that P height is 141.4 minus 98.8. So here, from my calculator, 141.4 minus 98.8, I have 42.6 millimeter. That is our height. So here, if I do have here the liquid mercury, that is the height here. And then the lowest here is this. So our height right there is the H. So P for gas is equals to P for atmospheres plus B of height, which is 764, yeah, 764.7 plus 42.6, 42.6, 764.7. I see 807 plus 3 atmosphere. So you need to remember when to add, when to subtract, when to add, when to subtract. It was a little bit tricky here, how you use 5. Sometimes you may just be given, the height. You don't have to worry about adding 5, subtracting 5. But the point here is always remember when to subtract the height, always remember when to add. And one other point is if you are given the atmospheric pressure in a different unit, than what you have here, or maybe the unit is in centimeters, you need to change to appropriate before you plug it in the equation. Well, I'll not spend time on looking at the blood pressure. At some point, you may have visited a doctor or you may have seen somebody. Even in grocery stores, there's some machine to measure the blood pressure. Blood pressure. And read in the text. All right, let's move on to section 6.3, the simple causes, and these are the cause laws. You can go ahead and start reading, make your own notes. Wells law, Wells law, Charles law, Avogadro's law, for ID, that's law. Just if you want to make your own notes, there is Dalton's law, of partial pressure. All right. These are the laws we will look at. And all these laws are generated or derived from 4 parameters or 4 identities: pressure, volume, temperature, and the number of moles. So we hold 2 constant, vary 2 of them from the 4. We end up with simple Cauchy laws describing the relationship between pairs of these properties. These are just properties we're going to look at. In the same sequence, this is what we look at, Poyer's law. I'll not ask you to explain or draw a diagram representing the J-tube and so forth. Ours is just only to understand, be able to define Poyer's law, right? And Boyle's this is the name of a person, Boyle. You should be able to state that the volume of a sample over gas is inversely proportional to its volume. So you should be able to define that. I've been writing that without just showing you. This is what I was trying to state. Just give you the meaning or stating the Poyer's law. I expect you to state. Yeah. It's just diagram on what he did. And this is a diagram or a plot of volume versus pressure. If you look at how the graph look like, at low volume, the pressure increase or decreasing the pressure. Decreasing the volume, increase the pressure, and vice versa. This is inverse proportion. Poyer's law states that the pressure of a gas is inverse proportional to its volume. Please learn, look at the plot or a graph of pressure versus volume. Look like a curve, right? But pressure versus 1 over V is a straight line. What that means is if we have 1 over V and pressure here, straight line graph. But if we have pressure, as you increase the volume, the pressure comes down. As you decrease the volume, the pressure goes up. This is a curved one. It's just curving down. It's just curving down that we have that. Well, this is what we call Poyer's law. P1, V1. If you want to see how it is, pressure is inversely proportional to 1 over V. You can say P equals to K over V. So if we have two conditions, let's say P2, 1, 1, 1, P2 equals K2 over V2. So if we cross multiply that and that, K1 equals to pressure 1 V1 is to derive this equation so that you know how that came. And K2 equals to P2 V2. So if K1 equals to K2, let's say P1 V1 equals to P2 V2. And the number of moles is constant, and number of moles is constant compared to the number of moles is constant and temperature is constant. What is changing here is the volume. The equation you see here, you can synthesize 4 more equations, which I don't recommend that you memorize, all right? Let's say if you want volume 1 is given by P2 V2 over P1. This is equation 1. Equation 2 is V2 equals to P1 V1 over T2. And then pressure 1 is P2 V2 over P1. And then P2 is given by P1 V1 over P2. So these are the equations you don't need to remember, but you can synthesize from the main one here to get the what you are looking for Poyer's law. You have seen subscript 1, subscript 2. This means initial condition 1, initial condition 2. For example, if the volume increased from 35 ml to 50 ml, right there, you should be able to identify V1 from V2, where you're starting is always designated as 1. Question will be the initial pressure and the final pressure. If the initial pressure is this, what's the final pressure? That means initial should be your P1 for pressure 1, final pressure should be P2, P2. Just to highlight some of the words you will see from Charles' law. So this is condition 2, condition 1. We'll also look at in Avogadro's law and Charles' law how the notation has been used, P1 or P2. Let's see problem here on using Charles' law. But before we do that, this is a diagram showing what happened when you decrease the volume, the linear relationship. Decreasing the volume, increase the pressure. You see pressure 2. Initially, before reducing the volume, pressure was 1 atmosphere. Reducing the volume by 1/2, it doubles the pressure. If the volume decreases, gas molecule collide with the surrounding surface more frequently, resulting in gas pressure. Yes, more molecules will combat the wall of the key. Therefore, high pressure, high pressure. Charles' law and diving, going deep sea, that for divers, for every 1 or for every 10-meter deep, there is 1 atmosphere change in it. Say that at a depth of 20 meters, the atmospheric pressure is 3 atmospheres, 3 atmospheres. So back to diving. Diving. So the divers have to exhale while rising, otherwise they risk decompression because of the pressure will drop drastically. It's recommended that they exhale while rising, out. So this is the relationship for Poisson law. P1 V1 equals to P2 V2. From my slides, I will or maybe you'll see in the exam that I'll give you something similar to what you see on the whiteboard. This N stands for number of moles, temperature, and it's constant, which is the same as what we have on the slide. So here are the plots you need to remember for Poisson law. Right, volume, pressure, inverse relationship. But when you say the reciprocal, there is the linear relationship. We have linear relationship. So have this. Hopefully, things will work out. Let's see an example here. All right, a sample of a gas with 5 moles, 2 significant figures at 1.0 atmospheres is expanded at a constant temperature from 10 liters to 15 liters. The final pressure is what? So here is a good example on how to find how to use Poisson law in solving problems. So here, you understand P1 V1 equals to P2 V2, the constant number of moles and pressure, and temperature. And temperature, this is what I was looking at. Number of moles and temperature constant is always outside. So we are looking for P2, which is the final pressure, is given by P1, V1 over V2. So long as using the right units, you should be fine. Don't let the number of moles confuse you. All we have to go is by the equation. P1 is 1.0 atmospheres times V1, which is 10 liters, over V2, which is 15 liters. Liters and liters will go away. And when you plug in the values, you should be able to get C 0.67. This is the correct answer, 0.67. So next, I may ask you V1 or V2. The easiest way to identify is to assign them that our final pressure should be P2. The volume change from 10 liters to 15 liters. So this is V1, this is V2. All right, volume 1, volume 2, so that you plug in the right place. And when you solve that, is 0.67 atmosphere, which is APM. Please look at problem number 33 on page 256. On page 256. Let's move on to Charles' law. Charles' law states that the volume of a sample of a gas is directly proportional to its absolute temperature. Remember, absolute temperature is Kelvin, is proportional to its temperature in Kelvin. So remember, volume has to be in Kelvin. If I derive that, V is directly proportional to T. That is condition 1. Let's say I have another condition, which is V1, direct relationship to we use proportionality constant. We say directly proportional. To get rid of proportional sign, let's say we introduce the constant so that V equals to K 1, 1. Likewise, for V2 equals to K2 if K1 and K2 equals to so if K1 equals to K2, K1 equals to K2, we could say V1 over T1 equals to V2 over T2. I don't like when it is like this, but if I can cross multiply, this will be V1 T2 equals to V2 T1, V2 T1 under constant pressure and number of moles. What I've done is I've derived Charles' law, and just like before, you need to read the problem and assign your notation as in V1 as in V2 T1 V2. If I was to derive individual equation, I'll end up with 8 so far. We'll find 1, 2, 3, 4. The first law had 4 equations you can synthesize. This one has 4 equations you can synthesize as well. Remember what is constant? The number of moles. Note, change the temperature, all right? Here, note, change temperature into Kelvin. All right? Which means degrees Celsius, K equals to degrees Celsius plus 273, and then we have that. Remember to use that. I'll cross multiply that to get this equation. I like when it is in this so that I can add that. So if we draw the straight line, the plot of temperature in degrees Celsius plus or versus volume, we end up with a straight line, of which if we extrapolate the temperature, all right, extrapolate the temperature, we end up with 273, some others use 273.15, we call it absolute value. Let's see, learning check a balloon. Helium balloon is filled to a volume of 5.60 at 25 degrees Celsius. What will be the volume of balloon if it is put into liquid nitrogen to lower the temperature from the temperature of helium to 167? So what you need to do here is, first of all, make sure that the units are the same. So if I look at what will be the volume? So this is V1. So V2, I'm going to use V2 equals to V1. We're using the equation here. This is the equation. We're using V1 T2 over T1. So the equation I'm using here is V2 is T1 V1 over T1 over T1. That's what we are looking for in this problem. First, convert pressure. Is it pressure? No, temperature. To Kelvin. They don't tell you, but they expect you to change this. So if I add that, it's going to be 273 plus 25 equals to 298K. So if we're looking for V2, so V1 here is what? V1 is 5.6. Liters times T2 is 70 of T1, which is 298. So this will go, that will go. And it's gonna be 1.4. and this is in liters. Because of the two significant figures, this will be one and the so because of the significant figures. Please look at page 256, number 35, number 36 on Charles law, just remember from this slide what is meant by absolute. If we extrapolate for different number of molecules, there is what we call absolute zero, which shows the temperature, the lowest possible. You can get from there. So this is an example on Charles law that the temperature affects the pressure of a gas. This is boiling water, it expands. In ice water, it will just shrink. It will just shrink. Okay. Now, Avogadro's number or Avogadro's law states that the number of moles is directly proportional. I mean, the volume of a sample of a gas is directly proportional to the number of moles. You should be able to say that. And just like in Charles' law, if we have Avogadro's law, so here, volume is directly proportional to the number of moles, And if we have two, let's say one, V2, remember we have condition 2 is directly proportional to number of moles too. So that V1 equals to Kn 1, V2 equals to K2 and 2. So that K1 over N1 and K2 equals V2 over N2. Which means V1 over N1 equals to, or rather if K1 equals to K2, we'll say V1 over N1 equals to V2 which you can cross multiply that to V1 N2 equals to V2 N1. This is Avogadro's. This is Avogadro's law, which relates the number of moles and the volume. Just like in the previous one, you don't need to memorize all the 4 equations you can synthesize here. And by the way, the number of moles and the pressure and temperature. So this is pressure. Pressure and temperature are constant. So you don't need to derive 4 equations out of the main one. I'll give you this in the exam. Yours is to just apply, all right? Yours is just to apply the equation and see what you are looking for, So for constant P and T, more gas, which means more molecules. A plot of volume and number of moles says a direct linear relationship. Direct as this one increase, or as you increase the number of molecules, likewise to the volume. The equation you see here, there is no difference with this. It's only that I'm cross multiplying the n so that it's very easy for me to look at what I'm looking for, making one of them the subject of the formula. The subject of the formula. So let's see, assuming that, let's see if learning check a cylinder with a movable piston contains 0.2 to 1 moles of gas and has a volume of 178 ml. What is the volume of what's the volume if an additional 0.244 moles of gas is added to the cylinder? All right. So here, all right, here, you need to know that this is your N1. So N1 equals to 0.221. V1 is 178. What is the volume if additional? So it means V2 equals to question mark because we are looking for V2. This is volume 1. We don't need to change the liters, but if you wish, that's fine. N2, we are increasing the original by 0.244, which is equal to 0.465. This is number of moles. So if we are looking for N2 or V2, V1, N2, or N2, V1, N2. So that's going to be 178 ml times N2, which is 0.465 moles. This is 6 over 0.2. This is 1 by the 2, 1. This is 375 ml. 375 ml. So what I've done here is just use the Avogadro's law, which relates to volume and the number of moles. N1, we are given here, V1, 178, V2, if the number of moles were added. This is Charles' law. Practice with problem number 37 on page 256 on Avogadro's law. Lastly, on part A, I'll look at the ideal gas equation, ideal gas law. We look at all the 4 parameters. If you look at the 4 parameters, there is temperature, there is the number of moles, there is the volume, and the gas. So it's assumed this PV equals to nRT. Where if you look at how this equation has been synthesized, it's a combination of Charles' law, Boyle's law, and Avogadro's equation. Before we look at an example, let's break down what is where this one is coming from. Here is the combination of all the 3 laws we have looked so far. Boyle's, there's Charles' law, there is Avogadro's law. One thing I want to point here is this is always, all right, this is volume in liters. This is always pressure in ATM, number of moles. And this is temperature in Kelvin. Please remember to change the temperature to Kelvin, and R here we call universal gas constant. We call this universal gas constant. And what we need to do is, or realize on this, is a units. There are 5 numerical values, but for gases, this is what we'll be using: 0.0820 liters times atmospheres over mole times Kelvin times Kelvin. The reason why we have, or the units right here, we see there is the liter, so we need to keep the volume in liters. Atmospheres has to be pressure has to be in atmospheres and temperature has to be in Kelvin, just the way I highlighted in this equation right here, that we need to have the pressure in atmospheres. This is because of the universal gas constant, Oh, well, down the line, you will have different values for R depending on what you are looking for. For today, this is our numerical value for R, numerical value for R in ideal gas equation. Remember what it is? R is called the universal gas constant, Probably solving one example on ideal gas equation, and I'll recommend that please, when I suggest problems, please go back, work on those on how to use ideal gas equation. Let's see, if the temperature, all right, if the temperature of a sample of methane gas, that is 10.34 grams in 50.0 ml, what in 50.0 liters vessel at 1 atmosphere. So if you look at this problem, we will have to work with temperature in Kelvin, and then we change to degrees Celsius. How? From PV equals nRT. And what we are looking for? Temperature. So temperature equals PV over nRT. Not deep, but we are looking for what? We are looking for temperature. PV, I'm dividing both sides by. Where, see, N is given by 10.34 grams of CH4 times mole. Mass of CH4 is 16.0. Is equals 0.6446. So once you know the number of moles, universal gas constant here, this is 2 liters times atmosphere. The rest we can plug in the equation. So temperature in Kelvin So temperature in Kelvin over number of moles, 0.644 moles times 0.0806 liters times atmospheres over mole times Kelvin. Make sure you get 984. Make sure you get 984. Kelvin. No, degrees Celsius. This will give you 1257.187 K. Therefore, degrees Celsius is 1257.73. It was equals to 984. Walk you through on how to use ideal gas equation. So here you have to look at the given mass. Like I said, if you are not given the period molar mass of the gas, you have to use the periodic table. That's how I let up in the previous slide here. 16.00 is the molar mass of methane. This gives us the number of moles of methane. Please look at problem 41, 42, 43, and 47. We'll come back again.